Hi YouTube, I'm Ben, and I'm going to go over a physics problem for converging lenses, and it'll use the lens equation. So, a lot of fun. Um, so what I have on the screen, I've got the problem. A 1 centimeter tall object is 75 centimeters in front of a converging lens that it has a 20 centimeter focal length. Calculate and show the image position and height. So we're actually going to start out with the show part first. So we're going to draw a ray diagram for this. And it'll give us a rough estimate of where our image will be. And to draw a ray diagram, you'll only need to draw three fundamental rays for a converging lens. So the definition of a converging lens is that any ray that goes parallel into the lens gets reflected through the focus. And because the focus is at 20 centimeters, we know the focus is right there, right there. So, and our object is this candle. I know it doesn't really look like a candle, but I'm not an artist. Alright, so we draw a ray from the tip of the candle to the lens. Now it's parallel to the x-axis, and that ray gets reflected right down through the focus, like that. The other ray that goes through a concave lens that we can draw without measuring angles goes right through the center of the lens and just keeps going. So that one looks like that. And the last ray goes through the focus and gets reflected parallel on the other side. And that would look like, goes through the focus right there, gets reflected. Oops, I'm gonna undo this. Here's the problem. Oops. Just gotta undo one of the rays, figure out how to. There, oops, went too far. Alright, so this one went through the focus, and we had a ray that went straight through the lens, like so. Then we had a ray, whoops. We had a ray that went through the focus and got reflected parallel on the other side, like so. And you can see roughly that all of these rays come together and form an image at this point. So that'd be the tip of the candle, and then we'd assume the candle would, be right there. So I'm guessing it's somewhere between 20 and 40 centimeters. I don't know yet, and we're going to find out using the equation I'm about to show you. So the equation is 1 over the focus of the lens equals 1 over the distance of the object plus 1 over the distance of the image. And this is all in meters. Just as a good physics habit, you don't want to use centimeters. It'll work, but it's not a good habit. So let's plug in all our information. So we know the focus is 20 centimeters, which is 0.2 meters. And we know that equals 1 over the distance of the object away from the lens, which is 75 centimeters, so 0.75 meters, plus 1 over the distance of the image, which is what we're solving for. So we take 1 over 0.2, so 5, minus 1 over 0.75 is equal to 1 over di. So we get that 5 minus 1 divided by 0.75 is 3.66 repeated, which equals 1 over di. So then we just flip it around and we take 1 divided by 3.66 repeated, and we'll get an answer. Distance of the image equals 0.273 meters. And now we know from our image that we drew that this is approximately right, because 0.273 meters is about 27 centimeters. So that would be 27 centimeters is where our image is located. So pretty simple. It's just plugging numbers into an equation. Now we need to find the height that it formed, the height of the image. And you saw the ray diagrams come together, it looks a lot smaller. So I'm expecting a smaller image than our original object. And there's also an equation to figure this out. So we know what we'll call magnification is equal to the height of the image over the height of the object, which is also equal to the negative distance of the image over distance of the object. And so we know 3 out of 4 of these right here. We know 3 out of 4. We know the distance of the image, we know the distance of the object, and we know the height of the object. And now we're just solving for the height of the image. So let's plug in. We're solving for HI. We know that HO is 1 centimeter, so 0.01. We know that's equal to a negative. The distance of the image was 0.273. Divided by distance of the object, which was 75 centimeters, 0.75. So just plug these into your calculator. And we get 0.00364, which is approximately equal to about 0.4 centimeters tall. So that's significantly shorter than our object. And keep in mind, this is negative. So what does that negative tell us? It's going to be in the opposite direction. So it's going to be inverted, like that. See how it's opposite directions? And that's how you tell an image is real. And that's a whole nother video. And I'll try and make an image, or make a video of real versus virtual images. But this is a real image because It's inverted. It has a negative height, as we might say. So we, in conclusion, have an object that is about 27 centimeters away, or I mean, an image that is 27 centimeters away from the lens and is about zero point 0.4 centimeters tall in the opposite direction as the object, which means it's inverted. Thanks, YouTube, and I hope this helped. See you next time.